Hello everyone, my name is Archana Devi. I am Assistant Professor from CSE Department, Rajagiri School of Engineering. So this video is for the subject System Software, which is a 5th semester CSE subject, BTech CSE subject. And the topic that we are going to see in this video lecture is from Module 2, Assemblers Part 2. So in the first part of this video lecture, we have already covered the introduction to assemblers, various assembler directives, various tasks performed by assembler, and various assembler data structures. So this is a continuation of that video. In case you haven't watched it, please watch that part first, so that you can continue with the second part. This is a part 2 where we will be learning about machine dependent assembler features. So as I have mentioned before, that this topic is taken from the textbook by Leland Beck, the System Software, an Introduction to System Programming. So yeah, the machine dependent assembler features. So in this, what we will be learning? We will be learning about the design and implementation of an assembler for SIC XC version. So we will see the various instruction formats and addressing modes and how exactly it's implemented. The assembler is getting implemented for the SIC XC version. So the topics that will be dealt in this video lecture are the various instruction formats and addressing modes, the translation of that into machine code, and then we will see a concept called as program relocation. So let's start with instruction formats and addressing modes. Okay, so let's have a quick recap of the SIC-XC architecture that we have already covered in the previous chapter in module 1. So if you would remember that the size of memory is 1 megabyte, which is 2 power 20, and the various registers which are there in SIC-XC are totally these many number of registers you have, where A, X, L, PC and status word are there already in your SIC architecture. The extra registers are the base. We have 4 extra registers in SIC-XC. They are base register with the register number 3, value 3, and you have 2 general purpose registers which will be used in some instruction for storing temporary data, and its values are 4 and 5. And you have an extra register floating point accumulator. This is used for storing floating point number. So the difference, there is one difference in size in floating point accumulator register. It is of 48 bits compared to all other registers where its size is 24 bits. So this you have already seen before. Then again we will have a recap of the various instruction formats in SIC-XC. So there are 4 formats. Each format, in the first format, it's of 8 bits or 1 byte each, where you only have the opcode specified in the instruction, example TIO. Then in format 2, it takes 2 bytes, altogether 16 bits. So the first 8 bits correspond to the opcode, and the remaining 4 bits each is used to represent the registers that is used in the instruction. So an example is add R, R1, R2. In format 3 and 4 are similar. The only difference is you have a 12-bit displacement field coming in format 3, whereas it's a 20-bit address field directly specified in the instruction in format 4. And these various fields which we have, NI, X, BPE, here the E field will be a 1 in format 4, whereas it will be a 0 in format 1. And all other bits, they correspond to each of the addressing modes which we have in SIC-XC. So N stands for indirect addressing, I stands for immediate addressing, X stands for indexed addressing, B stands for base relative, P stands for PC relative, and E is exponential addressing, which is used to represent the format 3 and 4, distinguish the format 3 and 4. And there is also a difference in format 4 instruction. You will have a plus sign before the opcode symbol. So here the opcode is also represented only in 6 bits, whereas in format 2 and 1 it's represented in 8 bits. The first 6 bits are being stored as opcode value when you represent the instruction in format 3 and 4. So let us look at the various addressing modes that we have. The first one is indirect addressing. Again, this is a recap because you have already covered all these addressing modes in your SIC-XC architecture. So in indirect addressing, you will have this @ symbol along with the displacement mentioned in the instruction. Then the immediate addressing, you have hash symbol in the instruction. Then you have PC relative or base relative. Given an instruction of the form OPM, this can either mean PC relative or base relative. Depending upon the displacement, the range of displacement, you will distinguish as PC relative or base relative. Again, this is a format 3 instruction. If this displacement cannot fit into 3 bytes, then it is extended to the 4 byte format, 4 bytes, which is in the format 4, you have 20 bits altogether in order to represent the address field. Why 20? The maximum number of bits that will be needed in order to represent an address in SIC-XC would be 20, because the memory size is 2 power 20. That is why an address will not go beyond 20 bits. So in format 4, the address is directly represented in the instruction. In format 3, it's a displacement, it's a partial address being represented in the instruction. So this extended format that we have in your 4 byte instruction format, you will have a plus symbol before the opcode. Then for indexed addressing, along with the displacement, you will have the value of index register as well in index register, indexed addressing. So this can either be a base indexed addressing, where you directly add the value of index register to the displacement, or this can be combined with PC relative or base relative. Then in SIC-XC, you have register to register architect instructions, which is quite faster because you are directly taking the value from the register rather than locating it from a memory location. Then finally, since we have larger memory in SIC-XC, 2 power 20 altogether we have, so it supports multi-programming. So multi-programming, multiple programs being executed parallelly. So that is a concept where we will be seeing in program reallocation. Okay, this is program reallocation. Okay, so let us look at a sample SIC-XC program. So a similar SIC program you have seen. So by looking at this program directly, you can locate various differences. For example, you have a hash symbol coming here, you have a plus symbol coming here, which denotes the format 4. Again, hash represents the immediate addressing. Then you have @ which represents indirect addressing. So this is in SIC-XC, it has been written differently with all the different types of addressing modes being used in the instructions. The same program that you have seen before is being modified in order to make use of all the addressing modes supported by SIC-XC. Equivalent program with its object code. When this program is being translated to its machine code, how does it look like? And you can see that the program is being loaded from the location 0. In the previous case, the program was getting loaded from the location 1000, but here it is loaded from the address 0, which will help you in order to perform multi-programming, which we will see towards the end of this video lecture. So here you can see some of these object codes are of 3 bytes length, whereas you have 3 object codes which is 4 bytes length, which correspond to format 4 instruction. So here you can clearly see that there is a plus symbol. Okay, this here also you have a plus symbol coming in the, it is not there, but here also you will have a plus symbol. And you can also see the addresses, yeah. And one more thing, here if you see STL RET ADR, RET ADR points to this location 0030. So in SIC, directly we used to write that address 0030 in the object code, but here you can see that it is not the value, it is some other value. So that's what I meant, we are not directly mentioning the address in the operand part. we are only mentioning the displacement, the relative distance of this instruction from this location. So if you subtract 0030 from the value contained in the next instruction 0003, you will actually get 02D. 02D. This is the distance between this instruction, because this instruction takes 3 bytes length. So you will subtract 0030 from 0003. So this is a hexadecimal value. So if you subtract 002D with 003, you will in fact get 02D, which is a 12-bit value. Okay, that is a displacement which you are storing in the object code, in the when this is getting converted to its object code, displacement value. So similarly for other cases also it's the same, where you are storing the displacement, the relative difference between the instruction and the location where it points to. So we will see various translation of instructions, how SIC instructions are getting translated. So different examples or different cases we will take, and one by one we will try to understand. The first one, how to translate the basic register to register instruction, which is your format 2 instructions. So in format 2 instruction, it takes 2 bytes, where the operand, the opcode takes 8 bits, 1 byte, and the registers which is mentioned in the instruction takes 4 bits each. So here you can see COMPR has opcode value A0, and the register number of these two registers are directly represented in the object code. A accumulator register has a value 0 and S has a value 4. So it's getting directly converted to its this is how it's getting converted to object code. So what does the assembler do? It converts a mnemonic operation code to its machine language equivalent using optab, by making use of optab, and it converts each register equivalent to its numeric equivalent. So the symbol table will be loaded with these registers. So along with all the labels that you have, the registers will also be loaded into the symbol table with its values. So the assembler can easily convert the registers into its equivalent numeric value. Now the next instruction of type in OPM. Okay, so as I have mentioned before, instructions of this type will either be assembled using PC relative or base relative addressing mode. Instructions of this type will either be assembled using PC relative or base relative addressing mode. So depending upon the displacement range, the addressing modes are being used. If the value of displacement falls within 0 and 4095, which denotes unsigned integer numbers, then base relative mode will be used. So between 0 and 4095. So altogether you have 4096 values. So since the displacement field is of 12 bits in format 3, 12 bits means 2 power 12 possible values you have, which is 4096. That's why it's between 0 and 4095. If the displacement that you are calculating is a signed integer value, then its range will be between minus 2048 to plus 2047, since it's a signed integer value. So if it's a signed integer value and the displacement range falls within this range, then you will go for PC relative. So what we'll do is we'll get the target address when this displacement is added to the contents of PC or the base register. That's how the target address is being calculated. This displacement will be added to the contents of either PC or base register depending upon the addressing mode. And if the okay. So now if the displacement can be fit into 12 bits, then format 3 will be used. But if the displacement goes beyond 12 bits, for such type of instructions, format 4 is used with a plus symbol. So there no displacement is calculated. Okay, please understand this. It's not displacement. Directly the 20-bit address is being stored in that field. Directly the 20-bit address will be stored in format 4 in the address field. So now we'll try to understand how given an instruction of this format, whether it is PC relative or base relative and how it's getting translated, we'll understand that with an example. So let's take the case where we are trying to calculate the displacement for program counter relative mode, PC relative mode. Okay. So the first step that the assembler would do is, given an instruction of this type, this is OP followed by M. Given an instruction of such type, the assembler will first try to verify if it is PC relative addressing mode. And for PC relative addressing mode, you will remember that the displacement should fall between minus 2048 to 2047. If the displacement doesn't fall into that range, then the assembler would try to decode it using base relative. That's the step. So first we'll check for the displacement value in PC relative. So if the opcode and memory address is given. So here you can see, if you look at the instruction STL RET ADR. So we don't know whether PC relative is used here or whether base relative addressing mode is used here. So what will you do? Calculate the displacement. So we know the target address in PC relative addressing mode. The target address is calculated as the contents of PC plus the displacement given in the instruction, right, plus the displacement given in the instruction. So here displacement we don't know how much, but the target address we know. What is the target address? Here STL RET ADR. So the target address is the address that points to RET ADR. 0030 is your target address, right, because that's where you are going to get the value from. So this is your target address 0030, and the contents of PC also we know, because for this instruction the address is 0000 sorry, and PC will point to the next instruction. So the contents of PC is 0003. So if you substitute the contents of PC, you can calculate the displacement value by subtracting the target address with displacement. So the target address with displacement, when you subtract, you will get 002D. So this displacement clearly falls under the range within 2048. So that means here they have used PC relative addressing mode only. Now you can easily translate this instruction to its equivalent object code by filling all the fields in format 3. Okay. So with the displacement calculated as 02D, let's try to fill in the values in format 3. So the opcode, which is 6 bits, the opcode value for STL instruction is 1414. So since you only have 6 bits, the last 2 bits for of the number 4 is not getting stored. So 1 is getting stored as such 0001, and in 4 you have 0100. So that is not getting stored in here. Then the various fields NIX BPE. So it's neither indirect nor immediate. That's why you have 1 1. Then index mode is not used. It is not base relative. It is PC relative. That's why you have a 1 bit here, and it is not format 4. Hence 0 in the E field. And finally, the displacement, which is 12 bits, you are storing the value 02D. So this is 0. This is 2. This is followed by D. This is the object code in binary. I've written it as such here, and its equivalent hexadecimal value 17202D. That's the object code which is being assembled by the assembler, which we have seen in the previous slide. So now let us look at another example where again this PC relative addressing mode is used for the instruction JC loop. So the same steps we'll do. We know that the target address is calculated as the contents of program counter plus displacement, where displacement becomes the target address minus the contents of PC. So here JC loop, the target address is the address that points to C loop. C loop is the address 0006, and the contents of PC. So since it's an instruction JC loop, the program counter will point to the address 001A. So your target address 0006 equal to the contents of PC 001A plus displacement. So here if you calculate the value of displacement, if you subtract these two values, you will get minus 14. Since the negative numbers are represented in 2's complement representation, the equivalent 2's complement representation of minus 14 is FEC in hexadecimal. So here you can see the 12-bit displacement field is being represented as FEC. So you can draw that format 3 instruction format and fill in the various values and cross check if you are indeed getting this value as the object code. Okay, so now let us look at an example for an instruction where the displacement is getting calculated with base relative addressing mode. So this instruction STX length. So we have this instruction over here, STX length. So as I told before, the assembler would first try to decode this using PC relative. So with the formula, target address is equal to contents of PC plus displacement. The displacement will be calculated as target address minus contents of PC. So for the instruction STX length, the target address is the address that length points to. Length points to 0033. And the contents of PC is the address 1059. For this instruction, PC will point to this instruction 1059. So if you subtract the target address with the contents of PC, you will get this value minus 1026 in hexadecimal, which is indeed minus 4134 in decimal. So you all remember that for PC relative mode, the displacement, the range of displacement is between minus 2048 to 2047. So this range falls beyond that. Hence, the assembler would know that here PC relative cannot be used and it goes for base relative addressing mode. So as base relative mode is used, now the formula is target address is equal to the contents of base register plus displacement value. So the target address for this instruction STX length points to the address 0033. So the target address is 0033 and the contents of base register. So the contents of base register can be loaded with an assembler directive called as base. Base followed by an operand value. So here whatever value you give here, okay, length contains the address 0033. Length points to the address 0033. So this value will be loaded to the base register. For that purpose only we use the assembler directive base. So now base contains the value, base register contains the value 0033. Displacement is calculated as target address minus base, that is 0033 minus the contents of base register is also 0033, which gives you the displacement value as 0. So this falls under the range of displacement for base relative, which is between 0 and 4095, right? So with these values we can easily fill the various bits in your format 3 instruction for STX length. So the opcode for STX, if you take from if you look at the appendix, you will get it as 10. So in the opcode field, the first 6 bits of 10 will be stored. So this is 1 followed by 0, 0. The last 2 bits are not stored. Then under N and I, you are storing 1 and 1 as it is neither indirect nor immediate. Then the indexed mode is not used. Base relative is used. Hence you have a 1 here. Then for P and D you have 0, 0. And as the displacement is 0, in the displacement field you have stored the value 0. So this is the object code in binary, which will be converted to, which will be stored as hexadecimal value. So if you try to decode this into hexadecimal value, you will get the answer as 134 followed by 3 zeros. So this is how the instruction is getting decoded to its equivalent machine language using base relative mode. So the assembler directive, which I mentioned in the previous slide, base, it tells the assembler what the base register will contain. You have one more assembler directive called as Nobase. So once base register is being loaded with a value using the assembler directive base, unless and until you use the statement no base, the assembler will keep on use the same value for all the instruction that makes use of the base register that follows after this instruction. So if you use the assembler directive no base, it tells the assembler that the contents of base register can no longer be used for addressing. So until this instruction is this assembler directive is used, all the instruction that follows the instruction that tells the assembler that base register is to be loaded with a particular value will use that same value in those instructions. Now let us try to translate an instruction with immediate addressing mode. So as mentioned before, in immediate addressing mode, you have a hash symbol coming along with the opcode along in the instruction. Say look at this example, LDA followed by #3. So this is your operand value. So if immediate mode is specified, then the target address, whatever is the displacement, becomes the operand. You don't have to fetch anything in from anywhere. So directly this will be represented in the instruction as a operand. So for the instruction LDA, the opcode is being stored, then it is not indirect, hence the value 0. Since it is immediate, the value 1 is stored. Indexing mode is not used, it's not base relative, it's not PC relative, and it's not format 4. And the displacement value, in the displacement field, value 3 is getting stored, 003. So this is object code in binary and its equivalent object code in hexa, 010003. That's how immediate mode is getting translated into object code. This is another example where immediate mode is used in a format 4 instruction. So plus denotes format 4 instruction. Just recollect one thing, that in format 4 instruction, the displacement value is the address. Okay, whatever value you give is the address. It's not the partial displacement value. So since 4096, which is 1000 in hexadecimal, will not fit in this address field. Okay, in format 3 instruction, this will not fit into your 12-bit field. That's why you go for format 4, which uses 20 bits for the displacement field. So for LDT, the opcode value has been filled. Then all these bit values, n is not 0, it is immediate, hence 1. All these fields are 0. Since extended format is used, this field is also 1. And the value is 1000 in hexadecimal. So 0, 1, 0, 0, 0. That's how you fill the displacement field. Now if you convert this binary value to hexa, you will get 7510100. This is the object code getting generated. So with that, we have come to the end of the feature at instruction format and addressing modes. Now let us look at program relocation. So this program relocation is, we load the program into memory wherever there is a room. So due to this property, we can load several programs into memory, and it can be run at the same time. That is sharing of the machine between programs, which is a multi-programming concept. So the actual starting address will not be known until the load time, right? Because you can load the program wherever there is room. So it's not specifying a fixed address at assembly time. Until now, what we have seen is absolute location, where we are loading the program at a fixed address. But in this case, we will not know the fixed address during the assembly time. So as base relative mode is used, now the formula is target address is equal to the contents of base register plus displacement value. So the target address for this instruction, stx length points to the address 0033. So the target address is 0033, and the contents of base register. So the contents of base register can be loaded with an assembler directive called as base. Base followed by an operand value. So here whatever value you give here, okay, length contains the address 0033. Length points to the address 0033. So this value will be loaded to the base register. For that purpose only we use the assembler directive base. So now base contains the value, base register contains the value 0033. Displacement is calculated as target address minus base, that is 0033 minus the contents of base register is also 0033, which gives you the displacement value as 0. So this falls under the range of displacement for base relative, which is between 0 and 4095, right? So with these values we can easily fill the various bits in your format 3 instruction for STX length. So the opcode for STX, if you take from if you look at the appendix, you will get it as 10. So in the opcode field, the first 6 bits of 10 will be stored. So this is 1 followed by 0, 0. The last 2 bits are not stored. Then under N and I, you are storing 1 and 1 as it is neither indirect nor immediate. Then the indexed mode is not used. Base relative is used, hence you have a 1 here. Then for P and D you have 0, 0, and as the displacement is 0, in the displacement field you have stored the value 0. So this is the object code in binary, which will be converted to, which will be stored as hexadecimal value. So if you try to decode this into hexadecimal value, you will get the answer as 134 followed by 3 zeros. So this is how the instruction. So this is an example for relocatable program where this program is written with using SICXC. So let us look at the instructions and see whether this has the same problem as the previous one. In this case, we can see the difference that the program is being loaded from the location 1000. Okay, it's not from 1000. From the location 0. It is not from a fixed location 1000. So if you write a program in such a way, then this says that we can load the program anywhere in memory. It need not be starting, it need not be at a particular location. It can be stored at any location if we write it starting from the address 0. So how is it achieved, or how can we say that there is no problem? So if you look at the same instruction, say let me take this STL instruction itself. Here you can see that STL RETADR points to the location 0030. But if you look at the object code translation, this does not have 0030. Instead, it has some other value. So how does this object code gets generated? So if you recollect, in SICXC, we have 4 formats of instruction. Format 1, which is of 1 byte, format 2, which is of 2 bytes. So all these instructions are of 3 bytes, and this instruction alone is of 4 bytes. So 3 instructions we can see with a plus symbol. Those 3 instructions alone are of 4 bytes, whereas all other instructions in this page is given as 3 bytes. So in that 3 bytes, the last 12 bits, that is the 02D, does not signify an absolute address. It actually signifies the displacement value. So this 02D is not an address. It's a displacement value of this location, RETADR, from the actual address. So that's how this displacement is calculated depending upon the addressing mode used. So in this instruction, it uses PC relative. So how exactly we get this 02D is the RETADR. We know that the target address is 0030. So we get the target address as the contents of PC added with displacement. This displacement distance, the contents of PC added with displacement. So you will get the displacement as target address minus contents of PC. Okay, I hope you are able to map this part. So the target address minus the contents of PC, target address of RETADR is 0030, and this is hexadecimal value. So if you subtract it from 3, you will get the answer as 02D. So that displacement is what you are storing in this location. It is not an absolute address. So in that case, all format 3 instructions will not have a problem, even if you load the program at any address. Suppose if you load the program starting from address say 1000. So all these addresses will change from zeros to 1000. Okay, so what will be this displacement value? The target address now becomes 1030. and the contents of PC is 1003. So if you subtract 1030 from 1003, you will still get the distance as 02D. So it's a relative distance. It is not an absolute value that we are storing in format 3. It's the case for all format 3 instruction. So if you want to check it with any other instructions also, you can cross check it. Say LDA length. So this length points to the instruction 0033, right? And for this instruction, the contents of PC is 000D. It points to the next instruction. So if you subtract 0033 from 000D, right? From 00D, you will get it as 026. Okay? So it's hexadecimal subtraction. You can verify it once. So hence, even if you load the program at any location, all format 3 instructions will not have any problem, as the relative distance or the displacement is being stored in the address field. Now let us look at format 4 instructions. So if you look at format 4 instruction, hope you recollect that the last 20 bits, in the last 20 bits, that is starting from here 01036, this is an absolute address. Format 4 supports storage of the address directly in the instruction. It is not a partial address like your format 3 where the displacement is being stored. In format 4, we are storing the address as such. So format 4 instructions will have a problem with relocation. Why? Because in this case, plus JSUB RDREC. Here RDREC points to the location 1036, which is not there in this diagram. Okay, so it points to the location 1036 RDREC. So what happens is, if you load the program in the location, say starting from 1000, this address will still remain the same, because here RDREC, the address location is 01036 itself when it got converted to the object code, because it is a absolute address which is getting stored here. So you but the address, it should be what it should be. If it is loaded from the address 1000, this address should change as 02036, right? Hence that is a problem with format 4 instruction. Now let us try to understand that with an example. So if you look at this diagram, here you can see this is a program module which is being loaded from the address 1000. So this you have this plus JSUB RDREC instruction which says 4B 101036 is the object code associated with it. So RDREC points to the location 01036. Okay, it is 01036. So now if this is loaded at the location 1000, then here it is 01036. Now what if it's loaded at the location 5000? What if it's loaded at the location 5000? Now RDREC points to the location 6036. It points to the location 6036. Here you can see that the instruction has changed accordingly. From the base address 5000, some value was added, right? And you got the address as 6036. Now what if the instruction is loaded into the location 7420? Now again here RDREC points now to the location 8456. So here you can see that this value is nothing but this displacement. If you subtract the target address from the base address, you will get the value as 1036. So in all the cases, to the base address, you are adding the displacement value. You are adding the displacement value to the base address in order to get the actual address. So even if it is located, even if it is the object code is generated as 01036, if you add that value to the base address, right? If you add 01036 to 5000, you will get 6036. You will get the actual address, right? So with the help of with some help, we can in fact relocate plus instructions, that is format 4 instructions also. Let's see that how. So the assembler informs loader about object code to be modified at the time of relocation with the help of modification record. So what is this modification record? We have seen the conversion of the assembly language to machine code, object code, which contains header record, text record, and end record. Now this program is being modified with modification record also. So the modification record, the column 1 denotes the letter M. Then the remaining 6 spaces, it's used to store the starting location of the address field to be modified. So in this case here we have to change this address, right? It is not 01036 if it is loaded to some other location. Then here the length of the address field to be modified. The next 2 bits contains the length of the address field to be modified. So it is mentioned in half bytes. So half bytes is nothing but 4 bits. 1 half byte means 4 bits. So here the 2 bits specifies some value in half bytes. Half bytes means 4 bits. So let us try to understand this with an example. So here you can see this instruction has to be modified. Suppose if you are loading it in some address. So all you have to do is wherever we have modification record coming, to that address you have to add the displacement value with the base address. That's what we'll do. So here you can see that the address of plus JSub is 006, right? So the object code 4B will be stored in the location 6. Next 10 will be stored in the location 7. Next 10 will be stored in the location 8, and 36 will be stored in the location 9. That is why in location 10, that is A, you have the next instruction. So this is a 4-byte instruction. So now starting from this 0 onwards, the address field is getting stored, right? The last 5 bits contains the last 5 locations contains the address field, which is altogether 20 bits. The last 5 location stores the address field. So that is why here the length of the address is written in half bytes. So here you can see that this 10 starting from this 0th location onwards you have to change, right? So that is stored in the location 007. That is the starting location 007. Then the length of the address field in half bytes. So this is half bytes means 4 bits. So this is 5 into 4. It's not 5 into 8 because it's not 1 byte, it is half byte. So 5 into 4 if you take 20 bits. So starting from the 7th location you have to modify the record. That's what it means. So this modification record informs assembler informs the loader with the help of modification record that this particular location has to be modified. Let us look at another example here. Plus JSub WRREC. So this has a again the first 2 locations stores the opcode. Then starting from 0105D, this has to be relocated, right? So the this value is being stored at the location 0014. That's why the starting address of the location address field to be modified relative to the beginning of the program. Okay, it's written related to the beginning of the program. It is 0014. Then again the next 5 bits, the 5 positions. So 5 into 4 mentioned in half bytes. The remaining 20 bits has to be modified. Similarly, one more instruction we have here. This starts at the location 0026. So the actual address will start from 0025. 27. So from there next 20 bits has to be modified. So with the help of a modification record, we can achieve relocatable program relocation even for format 4 instructions. So with that we have come to the end of assemblers part 2. So we have seen the various machine dependent features, instruction format, addressing modes, and program relocation. All these are called as machine dependent because it depends on the machine or the system. So I hope this session was informative. Thank you so much for watching.